Good evening and a warm welcome to one and all over here virtually and season's greetings to you. Hope you enjoyed the Christmas so well. I am Jismeri Jos, a faculty of the Department of Mathematics. It's my privilege and honor to host the 8th day of the International Webinar Series on various fields in mathematics, organized by the Research and Postgraduate Department of Mathematics in association with IQAC, Maharaja's Government Autonomous College, Ernakulam. Today we have with us Dr. Ramkumar P.B, Associate Professor and Head of Department of Mathematics, Rajagiri School of Engineering and Technology, Kochi, to give a talk on mathematical morphological operators on graphs and hypergraphs. Let me invite Dr. Shivakumar C, Controller of Examinations, Maharaja's College, to speak a few words.
Respected HOD Dr. Bloomy Joseph, convener of the program, Jismeri, chief guest and today's resource person, Dr. Ramkumar P.B, other faculty members and participants. Good evening to all and happy Christmas and happy New Year. First of all, let me thank the organizers, especially Dr. Bloomy Joseph, for inviting me to say a few words as a felicitation to this national webinar series. Mathematics department is one of the oldest department in Maharaja's College. It started its BSc program in early 1931 along with the other programs. Then started MSc program and later PhD programs. So this department, I will say that one of the leading, excellent department in our college, which produced so many good students over these years. Mathematics is a tough topic. It is very difficult to study mathematics for many of the students. And so many of the students will fail in mathematics, even in school classes as well as in higher classes. That is why teachers who teach mathematics and students who study mathematics have great respect all over the world. And also, we know that Srinivasan Ramanujan is considered as one of the greatest scientist and greatest intellectual India ever produced. He was a great mathematician. So mathematics is a tough, very difficult topic. This year, Department of Mathematics is organizing a lot of online programs due to the special situations of COVID pandemic. All these programs are extremely useful to its students. This particular webinar series, which is titled National Webinar Series on Various Fields in Mathematics, which is started its first talk on 5th December this year, which is a talk on topology of Riemann surfaces. This topic itself is an interesting topic, at the same time is a tough topic. The webinar series also included many interesting fields like fuzzy set theory, classification of surfaces, approximation in Hilbert space, and of course, Noetherian rings in abstract algebra. This Noetherian rings, which is named after M.E. Noether, a very famous mathematician, and one of her theorem, Noether theorem, is very fundamental in physics also, which will give you some relation between symmetries and conservation laws. So the webinar series is very vast, covering a lot of fields, and these fields have application not only in mathematics but also in other branches of science also. Today's lecture is by Dr. Ramkumar P.B. He is an associate professor at the Rajagiri College of Engineering, and he is going to talk on morphological operators on graphs and hypergraphs. And we know that morphological operations are the basics of image processing, etc. I'm sure the series helped the participants a lot to understand basic facts in fundamental mathematics. And I request all the participants, all the students to interact strongly with the resource person so that the idea becomes very clear. I hope the program will be a grand success, and I wish all the best to the organizers for conducting such a webinar series. So with this word, let me conclude. Thank you all.
Thank you, sir.
Thank you, sir, for your nice words. I cordially invite Dr. Bloomy Joseph, Head of the Department of Mathematics, Maharaja's College, to formally introduce and welcome the key speaker, Dr. Ramkumar P.B, to this event. Ma'am.
Good afternoon, all. Our eighth talk is going to handle by Dr. Ramkumar P.B, Supervising Guide, Abdul Kalam Technological University, Associate Professor and Head of the Department of Mathematics, Rajagiri School of Engineering and Technology. His areas of interest includes digital topology, mathematical morphology, graph morphology, hypergraphs, discrete mathematics, fuzzy sets and logic, etc. Published many papers in national and international journals, adorned different positions like PhD coordinator, coordinator of batch, etc. His inputs and contributions are just a phone call away. So, on behalf of all, I welcome Dr. Ram Kumar for the talk.
Thank you. Good evening. So first of all, I would like to take this opportunity to thank organizers of the program, IQAC of the Maharaja's College, Ernakulam, Department of Mathematics, especially Dr. Bloomy Joseph, Head of the Department, for giving me to deliver this talk. So the topic is mathematical morphological operators on graphs and hypergraphs. So first I introduce this mathematical morphology, binary morphology, gray level morphology, then lattice morphology, graph morphology, hypergraph morphology, and fuzzy morphology. So what is mathematical morphology? So ideas developed by Mathron and Serra in 1967. Basically, this morphology represents a set of tools for extracting features and combine tools to achieve complex operations. You can define morphological operators on binary images or on gray level images, and these are well-known nonlinear operators. So this is an approach for processing digital image based on its shape, and we can consider the geometric structure contained in an image. So basically the language of morphology is set theory. So mathematical morphology is an extension to basic set theory. So what is binary morphology? So in order to define binary morphology, consider mathematical definition of image. What is an image? An image is a mapping denoted by I from a set S of pixel coordinates to a set G of values such that for every coordinate vector P, there is a value I of P drawn from set G. A real image maps an n-dimensional Euclidean vector space into the real numbers. Here, pixel coordinates and pixel values are real. A discrete image maps an n-dimensional grid of points into the reals. Here, coordinates are n tuples of integers and pixel values are real. A digital image maps an n-dimensional grid into a finite set of integers. Here pixel coordinates and pixel values are integers. So when we consider a binary image, this map to two values 0 and 1. So this picture represents a digital binary image. Each square is 1 pixel. So foreground is denoted by 1. They are represented by using white pixels, and backgrounds denoted by zeros and given in black color background. So basically, when we consider a digital binary image containing two objects named as sets A and B, with respect to the position of pixel, we can represent these sets like this: B equal to, so this represents the set B equal to the position 0, 0, 0, 1 and 1, 0. And look at the position of set A. So corresponding to that position of pixels in set A, we can define set A in terms of pairs, set of set 5 0 3 1 4 1 5 1 3 2 4 2 5 2. So in order to define morphological operators on a binary image, we need to consider two sets, say sets A and B. So here sets in morphology represents the shapes of objects in an image, and the set of all black pixels in a binary image is a complete description of the image. When we consider the shape operators, usual union, intersection, etc. represent shape operators in binary morphology. So here x1 union x2, set intersection, set difference, etc. can be considered as shape operators. So in order to apply morphological operators, we need structuring elements. So what is a structuring element? So here the idea is we need to consider a shape mask. So this can be of any size and any shape, which can be digitally representable, having some origin. So we can assume that there is some origin to the shape. So a box, a square shaped box, hexagon, disc, or any shape, we can consider a structuring element like this. So common structuring elements are represented with respect to a sender contained in that shape. So this is a structuring element with respect to sender, square shaped structuring element, rectangular shaped structuring element, circular, disc, etc. So it can be of any shape. It's not necessary that structuring elements have to be symmetrical. Okay. So here in these examples, they are symmetrical with respect to origin. So it is not necessary. So here B equal to B tilde, that is when you take the reflection, that is denoted by B tilde. So this is an example of an image, binary image, and we can consider X as given image and B as a structuring element. The well-known morphological operations are dilation and erosion. So basically we have two operations, dilation and erosion, and when we use these operators continuously, we get several other operations, the composite operations known as closing and opening, etc. So we can construct other morphological operators using dilation and erosion. So what is dilation? When you consider an image and a structuring element, so here a dilation of an image with respect to a given structuring element is defined like this. It is dilation as Bx, it is equal to set of all B plus X such that B element of set B, XB element in R2, or we can consider it a set of all x such that Bx intersection x not equal to null set. So here, when we consider S as a given image, and if you consider this structuring element, apply this structuring element on this image in every pixel position, and apply this definition corresponding to Bx, we need to consider B plus x. So it is just like taking translation of every x with respect to this B element of structuring set B. So when we consider this structuring set, put this structuring set element in every pixel position, so like this. So if we put consider the structuring set inside the image with respect to the sender, we get the output like B plus x. So consider the length also. So place the structuring set like this and define a sender of structuring set, mark that point like this. So in the dilated image, this portion will also be included in that region. So apply the operator like this, the structuring element, and mark the point. So place the set structuring element like this, and then shade all positions with respect to the center of the structuring element. So after dilation, we can see that the size of image is increasing. So this is the effect of dilation. So it is the set of all B plus x such that B element of B. So consider another definition. When we consider set x and structuring set B, we can define dilation as union for every B element of B tilde xB, where B tilde represent the reflection of B, or in other words, this is x dilation B tilde. Therefore, when we consider various structuring elements with respect to the shape of structuring element, we get a dilated image. So place this structuring element in every pixel position of the image, and then take the translates. So it is like this. So finally we get a dilated image. So mathematically we can define dilation of two sets: dilation of image A or dilation of a set with respect to another set B. A dilation B or B dilation A is the set of all C in set 2 such that C equal to A plus B for some A element of A and B element of B. So here either A is acting as a structuring element or B is acting as a structuring element or set. So consider example, dilation with other structuring element. Okay. So when we place this structuring element in every pixel position and then apply the definition, so we get a dilated image like this. So dilation is the set of all points in the image where the structuring element touches the foreground pixels. So if the structuring element touches the foreground image, write a 1 at the origin of the structuring element. So here, when we consider binary morphology, binary dilation is acting like this, corresponding to input image, which is represented in terms of say 190, and if structuring element is like this 111 with respect to some sender 1, in the middle 1, we can consider this as the sender, and then place the sender in every pixel position. If this one is matched with 1 in the input image, then all elements in the neighborhood with respect to the length of structuring element become 1. Okay, so with respect to that position, that 0 become 1. So like that, place the structuring element in every pixel position so that we get output. So this is an example of dilation. So when we consider dilation, if B is an image and S is a structuring set, then dilate B S takes binary image B, places the origin of structuring elements S over each one pixel, and take the logical or structuring element S into the output image at the corresponding position. So if you assume that this as the origin of the structuring element, then place this structuring element in every pixel position. So here these elements are 0, but there is a 1 here. So place this 1, the origin of the structuring element at this point 1. Since there is a matching, since these two are 1s, with respect to the shape of structuring element, all elements in that set B become 1. So here these elements are also become 1. So this 0 become 1, this is already 1, and this is 1. Similarly, there is a 1 here, place this origin here. So this also become 1, this is also become 1. So this is the dilated image. So when we apply the dilation, you can see that number of 1s are increasing. That is, number of foreground pixels are increasing. So that is the effect of dilation, that fills holes, okay, expand shapes, fill gaps, gulfs, etc. So that is the effect of this dilation. Another morphological operation is known as erosion. So it is similar to dilation. So here dilation expands an image, a given image. So this is another example of dilation. So if you use this particular structuring element on this image, effect is like this. Okay. This is another example. So dilation can be defined in terms of translation. A dilation B equal to union for every B element of B. A with respect to translates B, A translate B for every B element of B, or union for every element of A, B A. So this is another example of dilation using a circular structuring element. So this rectangular shape region is a given image A, given set A, and use the circular structuring element. So place this circular structuring set in all positions, but at the boundary with respect to center of the circle, that portion will also be included in the dilated image. So that is the effect of this operator, dilation, and it satisfies several mathematical properties: commutative property, associative property, extensivity, and it is increasing. Then translation invariance property, linearity property, containment, decomposition. So these are the important properties of dilation. So here we can see that after applying operator, disconnected components become connected. So another example of dilation. So what will be the output? So here we have structuring an image is like this. We can assume that this is a structuring set with respect to sender origin. So apply this structuring set on a given image. Then again take a dilation with respect to a horizontal structuring set. What will be the output image? So that is the question. So when you consider the first set and the structuring set, vertical structuring set like this, place structuring set in every pixel position of the given image like this, and join a sender origin of the structuring set. So after applying this operation, so it is acting like this. So join all points. So we get a shape like this. Then again apply the operation, dilation operation on this image. So it is like this. Place the structuring set on every position, especially look at the boundary. It is acting like this. So we get a hexagon. Okay. Or in other words, we can decompose a hexagon into shapes like this. With respect to dilation, there is a decomposition for hexagon. Okay. Similar to this example, we have another example, a vertical and horizontal images. So we get a square like this. If you dilate with another square, you get another big square like that. So geometrically, we can construct several figures using dilation. And another important operation is erosion. So basically, erosion removes isolated noisy pixels in an image and smooths object boundary and removes the outer layer object pixels. So when we consider erosion, apply erosion, the effect is with respect to structuring element, origin of the structuring element, when there is a matching between the pixels given in the image, then the corresponding element become 1. Otherwise, that element become 0. So here, erode BS takes a binary image B, places the origin of the structuring element S over every pixel position and owes a binary 1 into that position of the output image only if every position of S covers a 1 in B. For example, if you consider image B and structuring set S, assume that there is origin like this, middle one, and place this one, origin 1 in any one of this image B. Okay, if there is matching, then that element converted to 1, otherwise that becomes 0. So here, with respect to the length of this structuring set, we can consider this position and this position, so that become 1 itself, but other element become 0 because there is no matching. When you place 1 here, this element becomes 0. So that is the effect of erosion. Okay, if there is no matching, that element become 0. So after applying erosion, we can see that number of zeros are increasing. So we can define erosion mathematically like this: A erosion B equal to set of all x in Z2 such that for every B element of B, x can be written as A minus B and A element of A, or it is set of all x in Z2 such that x plus b element of A. X plus b must be element of set A. So erosion shrinks the connected sets of ones of binary image. So we can use erosion for shrinking features, removing bridges, branches, etc. And another application of erosion is to get a boundary of the image. So just subtract eroded image from the original. So we get boundary of image. That is, boundary operator is defined as boundary of an image is original image is A minus A erosion B. So this is the original image A, and if you use B as a structuring set, apply A erosion B. This is A erosion B. Then take the difference A minus A erosion B. So we get image like this. So that is the effect of erosion. So a big disk and another small disk, we can consider this as a structuring set with respect to an origin. Apply the erosion operation. Okay, D represent the diameter. So place all structuring sets in every pixel position of the big disk, and then join the maximum region with respect to the origin of the structuring set. So we get a shape like this. So if you change the structuring set, we get some other figure. So it is like this. So place this here and take erosion. So output is like this. There are several applications to erosion. Okay, for region filling, we can use erosion to region filling, dilation and erosion. We can club these operations. And for getting skeleton and reconstruction, I'm not going to detail about this. If we use dilation and erosion one after the other, we get so many other operators. So important operators are opening and closing. Opening is defined as erosion followed by dilation. X opening B equal to X erosion B tilde dilation B tilde. So first apply erosion, then apply dilation. So we get opening of an image. So first apply erosion, so size of image will reduce, then apply dilation. So that is opening. So it is acting like this. Opening. We need to place the structuring set in every pixel position. So it is an erosion followed by dilation. It serves to eliminate noise. Does not significantly change an object size. Similar to this opening, we have another operator known as closing. X closing B is defined as X dilation B tilde, erosion B tilde. So first apply dilation, then apply erosion. So we get closing. It is acting on image like this. Place structuring set in every pixel position and apply the definition. Okay. So these are the properties of dilation and erosion, and it satisfies the duality property also. So when we consider operator, a dilation operation, take the complement and again take the complement. So we can define like this. If you apply phi of x complement the complement, so we get that image itself. So here x is the given image, take the complement x complement, then take dilation x complement dilation b tilde, then take the complement, so we get x erosion b tilde. So it is similar to applying De Morgan's law, and it satisfies the duality property. So we can decompose the structuring elements. We can assume that a given structuring element is a dilation of two structuring elements, say B1 and B2 tilde. So X dilation, B1 dilation, B2 tilde, you can write this as X dilation B1 tilde, dilation B2 tilde. Similarly for using erosion, so this is the geometry of decomposition. Okay, so this square shape can be decomposed like this, and this property can be applied to define another important operator known as hit or miss operation. So when we consider B as a combination of two structuring sets B1 and B2, we can use B1 to hit on white pixels, foreground pixels, which means that B2 miss white pixels and it will hit on black pixels, background pixels. That is why it is known as hit or miss, and it is defined as x hit or miss B equal to x erosion B1 tilde intersection x complement erosion B2 tilde, where we can consider B, structuring set B, as a combination of these two, B1 and B2. So we can apply these operators iteratively. Okay, A opening B is A erosion B dilation B, A closing B is A dilation B erosion B, and if you take closing, after taking closing, that is there will not be any change to the image. It is same as A closing B itself. Similarly, A opening B is A opening B opening B, and that property, since the shape is not changing, that property is called idempotent property. So these are the examples. Dilation with respect to structuring element. So you can see that number of ones are increasing. So after applying erosion, number of ones are decreasing, so like that. And there are so many other algorithms, operators, thinnings, convexal, pruning, etc. So when we consider gray level morphology, its framework is based on sets, a nonlinear framework, and we have to consider a maximum and minimum operation in order to define dilation and erosion. So here a set with element P such that it satisfies this partial ordering less than or equal to. The set of all subsets of a set S is a suitable set P, and define maximum operation using union and minimum using intersection. A binary image is a suitable set P. So we can apply gray level morphological operators on image like this a stack of binary images. So consider stack of binary images with respect to the positions like this. It is denoted by say f of 3, f of 3.5, f of 5, etc. So a function can be viewed as a stack of decreasing sets. So it is represented like this with respect to a parameter lambda. We can consider f of x as supremum of every lambda such that x element of x lambda f. So this represents stack of sets. So dilation and erosion of an image f of xy by a structuring element b of xy can be defined in terms of a maximum and minimum operation. So consider this example, the one-dimensional signal function f and a structuring element b. So if dilation b can be defined using maximum operation f of s minus x plus b of x such that x minus x element of domain of f and x element of domain of b. So this is the effect of applying this definition and then take the maximum of that. So we get dilation like this. So simply speaking, when we consider maximum gray level image, dilation operation is acting like this. Take the maximum within the window corresponding to a structuring element. So here 16 is the maximum, so all becomes 16. So here this partial ordering holds f less than or equal to g implies and implied by for all x f of x less than or equal to g of x. So basically when we consider phi 1 and phi 2 are dual operatives, phi 1 of f complement equal to phi 2 of f the whole complement, and f is less than or equal to phi of f, it is anti-extensive and idempotent phi of f equal to phi of f. Therefore, when we consider gray level images, a dilation can be defined as delta of f of x equal to maximum for every s element of s f of x plus s, and erosion is epsilon f of x equal to minimum for every s element of s f of x plus s. So here is an example, a grayscale line, scan line, and use a structuring element as a circular element. This C represents the effect of opening, and this represents effect of closing. So roll on this signal function. So this is closing f closing b, and this is f opening b. So when we consider any supremum of openings, it is still an opening. Any infimum of closings is still a closing. If we change the structuring set, we get output corresponding to that like this. So in this example, it is an opening by circular shape structuring element. Okay, this is the original image. Use this circular structuring element. So we get opening like this. So this is opening by circular structuring element. If you change the shape, we get opening like this. Okay. So we can define a morphological gradient like this in terms of dilation and erosion. So G equal to F dilation B minus F erosion B. This is the effect of this morphological gradient on an image. Now I'm moving to complete lattice framework for images and operators. So we can consider the lattice framework. Image processing operators can be viewed as a mapping from L to L, where L is the complete lattice of images under consideration. When we consider erosion, epsilon from L to M, L and M are lattices. There corresponds a unique dilation delta from M to L, such that epsilon delta is an adjunction, and this dilation is given by delta of y is equal to infimum of set of all x in L such that y less than or equal to epsilon of x. Dually speaking, corresponding to every dilation delta from lattice M to lattice L, there corresponds a unique erosion epsilon from lattice L to M such that epsilon delta is an adjunction, and this erosion is given by epsilon of x equal to supremum of every y element of M such that delta of y less than or equal to x. We can generalize this to any number of adjunctions. That is, for example, let epsilon delta be an adjunction between L and M, and let epsilon dash delta dash be an adjunction between M and N. Then there exists a adjunction epsilon dash epsilon and delta delta dash adjunction from L to N, L to N, by applying the composition operation. So we get adjunctions like this. So in lattice framework, dilation and erosion are defined using supremum and infimum. An operator epsilon from B to A is an erosion if it commutes with the infimum operation. Epsilon of infimum of xi equal to infimum of epsilon of xi for every I element of I. And here epsilon maps the greatest element 1 of B onto the greatest element 1A of A. Similarly, an operator delta from B to A is a dilation if it commutes with the supremum operation, that is delta of join supremum xi I element of I equal to supremum for every I element of I delta of xi. And we have several properties and statements corresponding to this lattice framework. There exists a relation connecting the lattices. That relation is denoted by rho, which is reflexive, delta n is extensive, where n represent the neighborhood under consideration, epsilon n is anti-extensive. So these are all equivalent statements, important statements, properties. And when we consider a granulometry on a positel which represent a family of operators, morphological operators is known as granulometry. So using granulometry, we can define several other operators. Here we can change the size of structuring set by introducing metric space theory into that. So we can define a distance metric to vary the size of structuring set. Using this concept of lattice framework, we can define a graph morphology and hypergraph morphology. So here in graph morphology, first we need to define structuring graph, which is analogous to structuring set in binary morphology, and we need a neighborhood function So when we consider a structuring graph denoted by S graph, an S graph A consists of a graph GA equal to VAEA, pair VAEA, and two non-empty subsets BARA contained in VA, respectively known as buds and roots. So matching an S graph A into graph G at vertex B amounts to finding a homomorphism theta mapping GA into G such that V element of theta of RA. Such a mapping theta is called an embedding of A into G at V. A neighborhood function is defined as NA V given that G equal to union of set of all theta of BA such that theta is an embedding of A into G at V. So consider this example. So this is the graph given, and denote root using an arrow and bud using this bold vertex. So we have several structuring graphs like this A, B, C, D, and consider NAV. So using structuring graph A, construct NAV. So place this structuring graph S graph on every position with respect to V, so that we have these possibilities. Similarly, for the other structuring sets, we get NBV, NCV, NDV, etc. And using this concept corresponding to a given graph, we can define dilution and erosion, a graph dilution and graph erosion like this. So use this structuring graph, place this structuring graph in every position. So look at the neighborhood adjacent vertices. So after applying dilution operation, you get a graph like this, and erosion of graph is this. So basically we have several operators on graph morphology: vertex dilution, vertex erosion, edge dilution, edge erosion, and graph opening, graph closing, graph half opening and half closing, etc. There are several operatives. Okay, so here I'm going to discuss about this dilation graph. In graph morphology can be considered like this. Consider operator delta dot x cross. Here this is the graph given, and take, so G is a graph, given graph, take a subgraph like this, x equal to x dot x cross. X dot represent the vertex set of x, x cross is edge set of x. Then apply the operator delta dot. So it is the dilation with respect to vertices on the edges of x on x cross, that is delta dot x cross is the set of all x in G dot, that is x in the vertex set of G, such that there exists edge, there exists EXY element of x cross. So apply this definition. So we get delta dot x cross. So this is delta dot x cross. Similarly, we can define epsilon cross x dot. Epsilon cross, so it is the collection of all edges operating on, so we need to consider edges on with respect to x dot, that is vertex set of x. So it is set of all EXY in G cross such that x element of x dot and y element of x dot. So this is epsilon cross x dot, epsilon cross x dot. And similarly we can define epsilon dot x cross. So it is a set of all x in G dot such that for all EXY in G cross, EXY element of x cross. So that is epsilon dot x cross. So this is epsilon dot x cross. And delta cross x dot is set of all exy in G cross edge set of G such that x element of x dot or y element of x dot. So these are the important graph operators, and we can define other operators, edge dilation of graph and vertex dilation like this, delta of x cross and epsilon of x cross, where delta is delta cross composition delta dot, epsilon is epsilon cross composition epsilon dot. Similarly, we have vertex dilation and vertex erosion denoted by delta of x dot and epsilon of x dot. So this is vertex dilation, edge dilation, vertex erosion epsilon of x dot, edge erosion epsilon of x cross, and by clubbing this dilation, graph dilation and graph erosion, we can define graph opening and closing denoted by gamma and phi, and graph half opening and half closing. So these are the important operators in graph morphology. So these are the important results regarding that lattice framework. So when we consider hypergraph morphology, we can verify whether two graphs are similar or not. So using dilation and erosion operation, we can define a similarity operation to check whether two hypergraphs are similar or not. Okay. So here the underlying space is a hypergraph consisting of vertices and hyper edges. And we can define a partial ordering on vertices and hyper edges. So a partial ordered set P of P under set inclusion, P of E under set inclusion, and there exists H equal to VE element of T such that if and only if V is contained in V, E is contained in this E, and X element of V such that there exists T in E such that and X element of E contained in V. So we need this partial ordering structure to order the elements in hypergraph, because in hypergraph structure we need to consider sub hypergraphs, and that gives us a complete lattice structure. So T less than or equal to is a complete lattice having smallest element and largest element. So ordering can be induced from sub hypergraphs and partial hypergraphs, etc. So when we consider a structuring element, here Bx can be denoted as delta dilation of a singleton set X. The structuring element can be interpreted as a binary relation between two elements. So here there is no need to consider a structuring set, structuring graph. Structuring element can be interpreted as a binary relation between two elements. So there is a trivial decomposition of V, vertex at V, as union for every X element of V singleton X. Similarly, there is a trivial decomposition of edge set also. So here is an example. So consider this hypergraph given the figure. So delta of E1, so consider delta of E1. So consider this hyper edge E1. Look at the edges connecting vertices in E1. Edges in connecting vertices in E1 are E1, E2, E3, E4. So delta of E1 is set E1, E2, E3, E4. Similarly, delta of E2 in the first figure, delta of E2. So we have E1, E2, E3, E1, E2, E3. And in second figure, delta of EI equal to set E1, E2, set E1, E2, E3. So in this way, we can define dilation and erosion on hypergraph. So dilation is a mapping from T to T dash such that delta of join I xi equal to join I dash delta of xi, and erosion is epsilon of meet I dash xi equal to meet I epsilon of xi. And structuring element we can consider in terms of binary relation. Bx is delta of singleton x, set x. So this is hypergraph H and a subhypergraph X. So similar to graph morphological operators, here also we can define dilation delta dot x cross, that is dilation corresponding to vertices, and take the vertex dilation on edges of x, vertex dilation. So delta dot is called vertex dilation. Epsilon cross is defined on x dot, that is vertices of x. So delta dot is a mapping from h cross to h dot such that delta dot x cross equal to union for every j element of j v of ej. Epsilon cross is a mapping from h dot to h cross such that epsilon cross x dot equal to set of all ei I in I such that v of ei is contained in x dot. Similarly, we can define epsilon dot and delta cross dilation with respect to edges. So it is set of all edges ei I in I such that v of ei intersection x dot not equal to null set. So delta dot x cross is the set of all vertices which belong to a hyperedge of x cross. Epsilon cross x dot is the set of all hyperedges whose vertices are composed of vertices of x dot. Epsilon dot x cross is the set of all vertices which do not belong to any edge of x cross. And delta dot x dot is the set of all hyperedges in h cross with at least one vertex in x dot. So apply the definition on x with respect to hypergraph H. So we get vertex dilation, edge dilation, vertex erosion, edge erosion, and combination of this. So we can define delta, epsilon, etc. And this satisfies the duality property also. So we have results regarding this. Delta double star and delta are dilations, then delta double star equal to delta, delta star star equal to delta. So these are the important results in hypergraph morphology. And we can define a formula to check the similarity of two subhypergraphs in terms of dilation. So this is the formula to calculate that similarity. So example is also given here. And we can extend this concept to fuzzy set also. So there is an extension known as fuzzy morphology, and generalization of fuzzy set theory is known as neutrosophic theory, neutrosophic set theory. So morphological operators are also defined on neutrosophic sets. So in fuzzy morphology, we can define T norm and T conorm to define dilation and erosion. So these are the references. Thank you.
Thank you, sir. Sridevi?
Yeah, can you hear me?
Yes, yes.
Okay, there
Yeah.
exists a question from YouTube, sir.
Yes.
The question is how to determine the size and shape of a structuring element for a particular image.
Size and shape, that we have to first we have to identify the properties of image. By trial and error method, we can identify the size and shape. Okay. So in application point of view, we have to apply the trial and error method. We have to identify best shape and size. So there is no fixed algorithm to identify that size and shape. Okay.
Is there any other question? You can put the in YouTube and Facebook. Sir, next question is
Okay.
is it possible to apply morphological operators on simplical complex?
Simplicial complex. Yes.
Simplicial
Yes.
complex.
Yes. It is possible. Similar operators are also defined on simplicial complex. There is an analogy in the case of a hypergraph and simplicial complex. So in application point of view, we can convert an image into a hypergraph or a simplicial complex, so that if you apply these operators, you can extract so many informations from an image. So that is the advantage of using hypergraph, and morphological operators on hypergraph plays an important role to extract informations.
Okay.
Thank you, sir.
Thank you, sir.
Okay.
Another question is it possible to use different structuring elements?
Yes, different structuring element, it is possible, and simultaneously we can vary the size. For example, if we use a circular shape structuring element, we can vary the radius of the circle uh, one after the other. That is, when you consider an image A and apply the structuring element having different radii. Okay, so the effect is different. So you can use, according to the situation, we can use different structuring element. When we alter the operators, first dilation, then erosion, then dilation, then erosion, then that forms a sequence of operation that is called alternating sequential filters. So in filter design, it is very important, because when we consider opening and closing operation, first apply the opening, then again apply the opening, there will not be any change in the image. So that property is called filter. So opening and closing is actually a filter, that is idempotent operator. And if you repeat this, that there will not be any change in the image. So when we arrange operators like this, that is called alternating sequential filters.
Okay, thank you, sir.
Okay.
സാറ് ഫസി സെറ്റിലേക്ക് ഇത് കൊണ്ടുവരാം എന്നൊക്കെ പറഞ്ഞല്ലോ ഫസി സെറ്റിനെ
Already
അപ്പൊ ഫസി അപ്പൊ നമുക്ക് ഡയലേഷൻ ഈ ഫസി ഗ്രാഫില് ഡയലേഷൻ കൊണ്ടുവരുന്നത് പറഞ്ഞല്ലോ, ഡയലേഷനും എറോഷനും. അപ്പം നമുക്ക് ഫസി ഗ്രാഫിലേക്ക് കൊണ്ടുവരാൻ പറ്റില്ലേ?
ഫസി ഗ്രാഫിൽ കൊണ്ടുവരാം, ഹൈപ്പർ ഗ്രാഫിലും കൊണ്ടുവരാം. അത് വർക്കുണ്ട്, ഞങ്ങളുടെ ഒരു വർക്കുണ്ട്, ഓൾറെഡി ഡിഫൈൻ ചെയ്യാം, കുഴപ്പമില്ല. അതായത് യൂസിങ് സെയിം കോൺസെപ്റ്റ് വി ക്യാൻ ജനറലൈസ് ദാറ്റ്. ഫസി ഇപ്പൊ ന്യൂട്രോസോഫിക് എത്തിയിട്ടുണ്ട്, അത് ഡിഫൈൻഡ് അല്ല ഇപ്പോ. ജനറലൈസേഷൻ ഓഫ് എത്തിയിട്ടില്ല. ന്യൂട്രോസോഫിക് ആണ് ജനറലൈസേഷൻ ഓഫ് ഫസി ഗ്രാഫ്. ഫസി സെറ്റ് തിയറി ആണ് ന്യൂട്രോസോഫിക്. അതായത് 3 മെമ്പർഷിപ്പ് ഡിഗ്രി കാണും. ഫസിയില് 1 മെമ്പർഷിപ്പ് ഡിഗ്രി ഉള്ളൂ, ന്യൂട്രോസോഫിക്കില് 3 മെമ്പർഷിപ്പ് ഡിഗ്രി ഉണ്ട്. അപ്പൊ അത് പുതിയ തിയറിയാണ്. അതില് ഗ്രാഫ്, ന്യൂട്രോസോഫിക് ഗ്രാഫ് വന്നിട്ടില്ല, ഗ്രാഫ് ഹൈപ്പർ ഗ്രാഫ് വരണേ ഉള്ളൂ.
പിന്നെ സാറ് തുടക്കത്തില് ഒരു സ്ട്രക്ചറിന്റെ സെന്റർ എന്ന് പറഞ്ഞല്ലോ,
സെന്റർ അല്ലെങ്കിൽ
ഒറിജിൻ എന്നുള്ള രീതി. അപ്പൊ നമ്മളതെങ്ങനെ ഇപ്പൊ ഒരു റെക്ടാങ്കിൾ ആണെങ്കിൽ, അല്ലെങ്കിൽ ഒരു കറക്റ്റ് ഒരു ഫിഗർ അല്ലെങ്കിൽ അതിന്റെ സെന്റർ എന്ന് പറഞ്ഞ് കാൽക്കുലേറ്റ് ചെയ്യുന്ന
പറ്റില്ല. അത് സിമെട്രിക് അല്ലെങ്കിൽ അത് നമ്മൾക്ക് ഇഷ്ടമുള്ള പോലെ ഡിഫൈൻ ചെയ്യാം. അപ്പൊ ഞാനൊരു എൽ ഷേപ്പുള്ള സ്ട്രക്ചറിങ് എലമെന്റ് കാണിച്ചപ്പോ അതിന്റെ മിഡിലാണ് ആ ഒരു 1 ആണ് ഞാൻ സെന്റർ ആയിട്ട് ചൂസ് ചെയ്തത്, നമ്മൾ ഒറിജിൻ ആയിട്ട് ചൂസ് ചെയ്തത്. അപ്പൊ അത് ചൂസ് ചെയ്യുന്നതനുസരിച്ച് ഔട്ട്പുട്ട് മാറും. നമ്മളത് ചേഞ്ച് ചെയ്ത് കഴിഞ്ഞാൽ ഡിഫറെന്റ് ആയിട്ടുള്ള, കാരണം ഇതാണ് കൊണ്ടുപോയി വെക്കണത്. മാത്തമാറ്റിക്കലി ഒറിജിൻ മാച്ച് ആവണം. അപ്പൊ 1 ആ ഒറിജിൻ ഏതാണെന്നുള്ളത് ഇമേജിൽ കൊണ്ട് വെക്കുകയാണല്ലോ ചെയ്യുന്നത്. അപ്പൊ സെറ്റിലെ ആ 1 കൊണ്ട് വെക്കുമ്പോൾ മാച്ച് ഉണ്ടെങ്കിൽ ബാക്കിയെല്ലാം സ്ട്രക്ചറിങ് എലമെന്റ് സൈസ് അനുസരിച്ച് ബാക്കിയെല്ലാം 1 ആകും. അതല്ലെങ്കിൽ അതെല്ലാം 0 ആകും. 0 ആയി എന്ന് പറഞ്ഞാൽ ബ്ലാക്ക് ആയി, 1 ആകുമെന്ന് പറഞ്ഞാൽ അത്രയും പോർഷൻ വൈറ്റ് ആയി. അതാണ് ഐഡിയ. മാത്തമാറ്റിക്കലി അതൊരു ട്രാൻസ്ലേഷൻ ആണ് നടക്കുന്നത്.
ബൈനറി ഓപ്പറേഷൻ തന്നെയാണോ അവിടെ നമ്മുടെ ഈ 1+1 0 എന്നുള്ള ബൈനറി ഓപ്പറേഷൻ?
ആ ഓപ്പറേഷൻ അല്ല, മാച്ചിങ് ആണ്. അതായത് 1ന്റെ പ്ലേസിൽ ഞാൻ കാണിക്കണോ? Here ഇവിടെ ഒറിജിൻ ചൂസ് ചെയ്യുന്നതനുസരിച്ച് ഷേപ്പ് വ്യത്യാസം വരും. കാണിച്ചത് ഈ ഇവിടെ ഒറിജിൻ ഈ സ്ട്രക്ചറിങ് സെറ്റില് 3 1 ഉള്ളൂ എന്ന് പറഞ്ഞാൽ ഇവിടെ 0 ആണ്, 4ാമത്തെ പൊസിഷൻ. ആൻഡ് ഒറിജിൻ എന്ന് പറഞ്ഞത് ഈ 1 ആണ്, മിഡിൽ ഈ സെൻട്രലിലുള്ള ഇത് എൽ ഷേപ്പ് അല്ലേ. അപ്പൊ ഇത് നമ്മളിപ്പോ സെറ്റപ്പ് എൽ ഷേപ്പ് ആണെന്ന് വിചാരിച്ചാൽ സിമെട്രിക് ആണെന്ന് പറയാൻ പറ്റില്ല. അപ്പൊ ഈ 0 കൊണ്ടുവച്ച് കഴിഞ്ഞാൽ ഒറിജിൻ കൊണ്ട് ഈ 1 കൊണ്ട് 0 വെച്ച് കഴിഞ്ഞാൽ മാച്ചിങ് ഇല്ല. അപ്പൊ അത് 0 ആയി തന്നെ തുടർന്നു. പിന്നെ ഞാൻ ഡയലേറ്റ് ചെയ്ത ഇമേജിൽ ഇതെങ്ങനെ 1 ആയി? ഇവിടെ മുകളില് ഫസ്റ്റ് റോയില് 2ാമത്തെ എലിമെന്റ് 1 ആണ്, അതെങ്ങനെ 1 ആയി? അതിന് ഈ 1 ഒറിജിൻ സ്ട്രക്ചറിങ് എലിമെന്റിന്റെ 1 2ാമത്തെ റോയില് സെക്കൻഡ് എലിമെന്റിൽ കൊണ്ടുവച്ചു, അത് 1 ആണല്ലോ. ആ 1ഉം ഒറിജിൻ 1ഉം മാച്ചായി. അപ്പം അങ്ങനെ മാച്ച് ആയി കഴിഞ്ഞാൽ നമ്മൾ ഇത് കൊണ്ടുപോയി വെക്കുകയാണ് സ്ട്രക്ചറിങ് എലിമെന്റ്. മാച്ച് ആയി കഴിഞ്ഞാൽ ആ സ്ട്രക്ചറിങ് എലിമെന്റ് ഷേപ്പിൽ എത്രത്തോളം 1 ഉണ്ടോ അത് അത്രയും ഈ ഇമേജിലും 1 ആകും. അപ്പോൾ ഇവിടെ ഇതിങ്ങനെ ഈ എൽ ഷേപ്പ് 1 ആയി. അതുപോലെ 2ാമത്തെ റോയിൽ 3ാമത്തെ 1 കൊണ്ട് വെച്ച് കഴിഞ്ഞാൽ അപ്പോഴും 1 ആ എൽ ഷേപ്പിൽ 1 ആയി. അങ്ങനെയാണ് ഈ എൽ ഷേപ്പ് ഇവിടെ ഇത് വന്നത്. ബാക്കി ഒന്നിലും മാച്ച് അല്ല, അപ്പൊ അതെല്ലാം 0 ആയിട്ട് തന്നെ മാറും. അതാണ് അതിന്റെ എഫക്റ്റ് ബൈനറിയിൽ. സെറ്റ് തിയറിറ്റിക് ആയിട്ട് പറയുമ്പം അത് എക്സ്റ്റെൻഡ് ആണല്ലോ, C = A+B ആണ്. അപ്പം A എലമെന്റ് ഓഫ് ഇമേജും B എലമെന്റ് ഓഫ് 2 സെറ്റ് ഉണ്ട്, അത്രേ ഉള്ളൂ. സെറ്റ് തിയറി മാത്തമാറ്റിക്കലി പറഞ്ഞ 2 സെറ്റ്, ജസ്റ്റ് ഒരു അഡീഷൻ അല്ല അവിടെ. അതാണ് ഡയലേഷന്റെ പ്രത്യേകത.
Thank you very much, sir. No more questions, I think.
Okay.
Thank you.
Thank you.
Thank you, sir. Thank you, sir, for the session.
Okay.
Now, it's vote of thanks section. I call upon Dr. Blomi Joseph to deliver the vote of thanks.
On behalf of all faculty, research students, PG and UG students of our department, I would like to convey my sincere gratitude to Dr. Ramkumar P.B. for sharing his deep knowledge in mathematical morphological operators. I also extend my thanks to Dr. Shivakumar C. for felicitating the talk. Dear participants, thank you for your esteemed presence. Now we move on to paper presentation session, and it will be chaired by Dr. Ramkumar P.B. Now Divya S.L., research scholar, Maharaja College, will present her paper.
Is the presentation clear?
Yes.
Okay.
Yes.
Put it in
Okay.
slideshow mode.
Okay, sir.
Okay. Yes. Okay.
So, okay, is this clear?
Yes.
So, I am Divya SL, a research scholar under the guidance of Dr. Blomi Joseph, research guide and HOD of the Department of Mathematics, Maharaja College, Ernakulam. I am doing the presentation on milk quality analysis using inductionistic fuzzy sets. So, inductionistic fuzzy set was introduced by Krasimir T. Atanasov. It is a generalization of fuzzy set, and it is an excellent tool to deal with the vagueness and uncertainty involved in the process of decision making. So consider a non-empty set capital X, then an inductionistic fuzzy set A in capital X can be defined as A is equal to set of all triples x, mu ax, nu ax, x element of capital X, where this mu a is a function from the non-empty set capital X to closed interval 0, 1, and it defines the degree of membership of the element x element of capital X, and nu a is another function from capital X to closed interval 0, 1, and it represents the non-membership degree of x element of X. So here for all x element of X, 0 is always less than or equal to mu ax plus nu ax less than or equal to 1. Excuse me, my screen is not visible. So next is, I couldn't move it.
Sridevi?
Okay.
Now, is this visible?
No.
Can
No,
you
it's
see
not
it?
visible.
Not visible?
Not,
You
not.
can't see
Sridevi,
it?
continue.
Okay.
We can't see.
You can't see the
Sridevi,
slide 4?
No, no, no. It's not shared actually. Share the screen.
Okay, please wait.
At the bottom. At the bottom.
Share screen. Share screen.
Yes.
Share the application window only.
Okay, okay, okay.
Then it will be more convenient to you.
Okay, okay. Actually, some problem with some app installed. Sorry
Now
for
there
this.
is no signal problem.
No signal. Signal is
Smooth. It's not
Please
problem.
wait. Please wait. Please wait.
Sridevi, play the uploaded one.
Okay.
The same
Okay.
thing.
Divya, I will share it.
Okay, okay, okay. Please wait. Excuse me. Please wait. Please wait. Okay, I will continue from the fourth slide onwards.
Okay.
Sorry for the inconvenience. So, after inductionistic fuzzy set, a definition of inductionistic fuzzy set, we have an important topic, inductionistic fuzzy set index. Its another name is hesitation margin. So, inductionistic fuzzy set index is defined as pi ax is equal to 1 minus mu ax minus nu ax. So this element, this value pi ax always belongs to the closed interval 0, 1. Pi ax expresses the lack of knowledge of whether the element belongs to the IFSA or not. Now, inductionistic fuzzy set is used in many real-life problems. Here, it is used to determine the suitable purpose of milk. It is used to categorize the raw milk for different processes or different products or uses. Now, this grading is achieved by finding the normalized Hamming distance between the two inductionistic fuzzy sets. Now, this normalized Hamming distance between two inductionistic fuzzy sets, A and B, is given by L dash IFS of AB is equal to 1 by 2n sigma I is equal to 1 to n modulus of mu A xi minus mu B xi plus modulus of nu A xi minus nu B xi plus modulus of pi A xi minus pi B xi. Now consider the set of samples S. So here we consider 3 samples S1, S2 and S3. So set S constitute the set of samples and set U, let U be the set of uses. Here we consider 3 uses of milk product. So health drinks, beauty products and fertilizers. And let A denotes the set of adulterants. Here we consider 2 adulterants, starch and water. Now in this table, here the categorization of milk is done based on the quantity of adulterants present in the milk sample or present in that particular use. So here for health drinks, based on experts' opinion, for health drinks, we are grading the starch content, or we are presenting the starch content as the triple 0.1, 0.7, 0.2. That means the membership value is 0.1, the non-membership value is 0.7, and the remaining, that means 1 minus 0.1 minus 0.7, that is 0.2. 0.2 is the hesitation or degree of indeterminacy or lack of knowledge. Now, the water, the adulterant water corresponding to health drink, we are grading the content of water or the quantity of water as, or we are assigning the values as 0.3, 0.5 and 0.2. That means 0.3 is the membership value, 0.5 is the non-membership value, and 0.2 is the hesitation margin. Similarly, for the cases of beauty products and fertilizers. So from this table, it is clear that when starch is very, very low and water is low, it is more suitable for using as health drink. Or in other case, when the starch content is very high, that means if the membership value is 0.8, 0.9, something like that, it is more suitable for using it as a fertilizer or fertilizing products. Now next is, so here we are taking 3 samples, S1, S2 and S3. So this table shows the samples versus adulterant, starch and water. Here also, like the above table, here also the sample S1, the starch content in the sample S1 corresponding to the starch content in the sample S1, we are assigning the degree as 0.8. So the membership degree as 0.8, non-membership degree as 0.1, and the hesitation is equal to 0.1. Similarly, for water, in this sample S1, the content of water is assigned as, the quantity of water is assigned as 0.2, 0.7, 0.1. That means membership value, the quantity of water in S1 is very low. So 0.2, 0.7 is the non-membership value, and 0.1 is the remaining hesitation margin. Similarly, for the case S2, sample S2 and sample S3. So here it is clear that S1, for sample S1, the starch content is greater than or greater comparing to the other 2 samples. The starch content is 0.8 and the water content is 0.2. So for S1, for sample S1, the starch content is 0.8, high compared to the other samples. And here S3, consider the sample S3. The starch content is very low, 0.1, and the water content is also low for that sample. Now we choose the normalized Hamming distance method, or we calculate the distance based on this normalized Hamming distance method. So L-IFS AB is given as this. So here we take the 2 inductionistic fuzzy sets as follows. A is the inductionistic fuzzy set representing the level of adulterants in the samples under consideration. And B is the IFS, which represents the level of adulterants present in the different categories. That means health drinks, beauty products, and fertilizers. Now here we are taking, or we are considering 2 adulterants, starch and water. So here in this case, for our case, N is taken as 2. Now, after calculating the distance between A and B, so that means the distance between sample S1 and health drink, the distance between sample S1 and health drinks is 0.45. The distance between S1 and beauty products is 0.35. And similarly, the distance between S1, sample S1 and fertilizers is 0.25. Similarly, we calculate the other distances for other samples also. So from this, it is clear that for the first sample, the least distance or shortest distance is 0.25. For the sample S2, the shortest distance is 0.15. And for S3, the shortest distance is 0.1. So that means we got the result as S1 is more appropriate for using as a fertilizer or fertilizing purposes, and S2 is appropriate for using it as beauty products. And similarly, S3 is more appropriate for using as health drink purposes. So that means the intuitionistic fuzzy set acts as an efficient tool in selecting the most appropriate product based on the quantity of adulterants present in milk. It can be utilized in the decision-making process involved in milk quality analysis. Also, it can be implemented in developing many quality controllers. These are the references. Thank you.
Okay. How you arrive at the membership degrees of starch and water?
So it is actually based on experts, industrial experts' opinion, and also on chemical experiments, sir.
Okay.
Shall I pursue next presentation, sir? Needu PR, research scholar, Maharaja's College, will now present her paper.
Thank you, Miss. Am I audible?
Yes,
Yes.
yes.
Is this presentation clear?
Yes.
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 Good afternoon. I am P.R. Neetu, research scholar under the guidance of Dr. Bloomy Joseph, Maharaja's College, Ernakulam. Here I am presenting a paper on fuzzy regularly closed sets in Michelake's fuzzy topology. As we know, fuzzy topological space was introduced by C.L. Chang in 1968. But this is only a natural translation of the ordinary topology to fuzzy sets. Later, in 1975, Michalik defined fuzzy topology in a quite different way. In this presentation, we took fuzzy topological space by Michalik as the basic structure for our construction of regularly closed sets. With this introduction, I am starting my presentation. This is the abstract of the presentation. As I said in the introduction, in 1975, Michalik introduced another form of fuzzy topology. Since the introduction of fuzzy topology by C.L. Chang, many work has been done to extend the theory of topology to fuzzy sets, but not much work has been done in the field of fuzzy topology by Michalik. In 1981, K.K. Azad introduced the concept of fuzzy regularly closed subsets of a fuzzy topological space in Chang's sense. This paper aims to introduce the concept of fuzzy regularly closed sets in Michelake's fuzzy topological space and study some of its properties. Just 1 second. To define fuzzy topological space, Michelake first defined the topological space in terms of function. As fuzzy set is defined as an extension of characteristic function, he defined fuzzy topological space as an extension of these functions. As per his definition, topological space is as follows. Let X be a non-empty set and P of X be the power set and U be a function from P of X to P of X that satisfies the following conditions. If A subset of X contains at most one element, then UA is equal to A. And if A1 subset of X, A2 subset of X, then UA1 union A2 is equal to UA1 union UA2. Then the pair XU is a topological space. This is just an illustration of how a topological space is defined by Michalik using function from P of X to P of X. Now to define fuzzy topology, Michalik extended the function U from P of X to P of X to P of X to F, where F is the set of all fuzzy sets in X. The definition of fuzzy topology by Michalik is as follows. Let X be a non-empty set and P of X be a power set and F be the system of all fuzzy sets in X and U be a function from P of X to F which satisfies the following condition. If A subset of X, then UA of X is equal to 1 for all X belongs to A. If A subset of X contains at most one element, then UA of X is equal to chi A of X, where chi A is the characteristic function of the set A. If A1 subset of X and A2 subset of X, then U of A1 union A2 of X is equal to maximum of UA1 of X, UA2 of X. Then the pair XU is called fuzzy topological space. As a trivial example, we can see that all non-empty set has trivially a fuzzy topological structure in Michelic sense. Here we take the characteristic function as U. C.L. Chang defined the interior of a fuzzy subset, but Michelic defined fuzzy interior of an ordinary subset. Fuzzy interior and fuzzy boundary of an ordinary set is as follows. Let XU be a Michelic's fuzzy topological space and a subset of X. Then the fuzzy set mu A interior defined by mu A interior of X is equal to 1 minus UA complement X is called the fuzzy interior of the set A. And the fuzzy boundary is as follows. The fuzzy set U delta A defined by U delta A of X is equal to minimum of UA of X, UA complement of X is defined as the fuzzy boundary of the subset A of X. Using this definition of fuzzy interior and fuzzy boundary, Michelic defined fuzzy open and fuzzy closed subset of a set. Also, he proved that a subset A of X is fuzzy closed if mu UA is equal to chi A and fuzzy open if mu A interior is equal to chi A. The fuzzy closed and fuzzy open defined by Michelic is as follows. Let XU be a Michelic's fuzzy topological space. Then A subset of X is said to be fuzzy closed if chi A of X greater than or equal to minimum of UA of X, UA complement of X for all X belongs to X. Let XU be a Michelic's fuzzy topological space, then a subset A of X is called fuzzy open if for every X belongs to X, minimum of chi A of X, U delta A of X is equal to 0 where mu delta A is the fuzzy boundary of the set A. This I already mentioned before. We have to note that in Chang's fuzzy topology, which is just a translation of topology to fuzzy sets, the interior and closure of a fuzzy set is defined, while in Michelic's fuzzy topological space, fuzzy interior and fuzzy boundary of a subset of X is defined. With these preliminaries, we define the fuzzy closure of a subset A of X as follows. Let XU be a Michelic's fuzzy topological space and let A be a fuzzy closed subset of X. Then the fuzzy set mu A interior defined by mu A interior of X is equal to minimum of UA of X such that UA complement of X greater than or equal to chi A of X is called the fuzzy closure of the set A. Here it must be noted that A is fuzzy closed in Michelic sense. Similarly, fuzzy regularly closed set is defined as let XU be a Michelic's fuzzy topological space and let A be a fuzzy closed subset of X. Then A is said to be fuzzy regularly closed if the fuzzy closure of the fuzzy interior of A is equal to chi A. This is the main theorem in this presentation. Let FRCMX be the set of all fuzzy regularly closed sets in Michelic sense. Then FRCM of X is a complemented lattice with complement defined as for A belongs to FRCM of X, A complement is equal to F closure X minus A, that is equal to X minus F interior of A. And the second theorem is FRCMX is a complete lattice. Similarly, we can define FROMX and prove that FROMX is also a complete lattice. As a conclusion, since the introduction of Chang's topology in 1969, investigate all areas of topology. But the fuzzy topology by Michalik has caught the attention of researchers very recently. In 2001, Francisco Galileo published a paper on Michalik's fuzzy topological space. Later, he published some work in 2009 and 2015. These are the references used for this presentation. With this, I conclude my presentation. Thank you.
Thank you, Neetu.
Okay. Is that lattice distributive? Lattice you have mentioned.
So,
It's complemented lattice, right?
yeah, complemented lattice.
Yeah. Complemented. Is it distributive?
Yeah, we have proved it.
Distributive also.
Hmm.
Okay. So, does there exist any other property when you consider a complete lattice and
It
complemented
can be a
lattice?
Boolean algebra too.
Yeah,
We
yeah,
can
that is right.
prove that
Because
it can be.
complemented distributive lattice is a Boolean algebra.
Yeah, it can
I
be a
think,
Boolean algebra too.
yeah, we can define some other operators in terms of this Boolean algebra. Okay.
Thank you, sir.
Thank you, Ramkumar sir, for sharing the event and for the excellent session you gave in mathematical morphological operators. You explained it very clearly. Thank you, sir.
Thank you.
Once again, thank you all. Have a nice day.
Okay.
With this, we conclude our today's session.